Hi, I'm Tom Stephenson, and welcome to our Residential Technology course. In today's lecture, we are going to be discussing building envelope, really building science. We're going to be getting into aspects or an introduction to building science in residential construction. And for the most part, we'll be discussing the elements of the building envelope. What is it? How do we insulate it? How do we design our buildings and our structures so that they provide a more energy efficient model and a healthier model for the occupants that are living in the buildings or structures. So some of the things that we'll be looking at, and this is really from chapter 12 of your textbook, and so we get into the information from chapter 12. So looking at how to interpret information from drawings, I have another video which is 8C, which gets into all of those aspects, explaining the basics of building science, as I mentioned, some of the qualities and functions of an air barrier and a vapor barrier, what are some of the nuanced differences between them as well. So I've had the good fortune in my career to get a lot of opportunities, and I did managed to coordinate the building science program at the University of Toronto, for about, I guess, close to 9 years. And so I got to work with a lot of researchers and building scientists, and we developed courses and programs and certification together. So I learned a lot from them. I by no means think of myself in that way. I'm more a practitioner and project manager, but the immense learning that came out of that was fantastic for me and for all the people that were involved with that program. So one of the things that really struck me was this whole concept of systems approach and thinking of our buildings like a system and thinking of our buildings like humans, right? You've got the structure, which is the skeleton, and we've looked at the structure when we've talked about framing of houses and the foundations and the footings, all those structural elements. And then we've talked about the building systems, and that would be your plumbing, your HVAC, your electrical systems, all of those aspects. And so if we think about that, that would be like the organs of a human, the heart, the liver, the kidney, the lungs, all of these types of things. And then if we want to think about it, the skin, all right, so our skin, the external elements, the exoskeleton, the outside of the building, the covering, and what separates the outside from the inside. And so when we think about it that way, that would be the building envelope. And when we think about humans, you know what? If you've got some sort of infection on your skin, the rest of you does not feel well. If the organs aren't working too well, the rest of you does not feel well. If you have a break in one of your arms, you're not going to feel too good. And so we think about buildings from that perspective, like a system. They don't operate too well, and they have problems, and maybe the air quality inside, you don't feel comfortable with it. Maybe if you've got a lot of problems with the envelope and you've got high humidity levels inside and the weather temperature is right, you've got mold growth, and then that's going to be not good for the occupants of the building. So we start thinking about our buildings as a system. That will be a good way to think about the building science approach, because there's all these variables that play into the system. When you go to see a doctor, you've got to figure out things. The doctor's got to figure out things. You see a GP, they got to figure out things. And if it's something more complex, they're going to send you to a specialist, but they try to narrow it down. What's the root cause of the problem, and go from there. So the house as a system, given this is a residential technology course, is a good way of thinking about things. The first time I heard of the house as a system was probably back in the 1980s when the R2000 program started, which is a high energy efficiency program. The idea was 2000 was a year way into the future, which is in the past now, but it was an excellent program for the time, and it really brought in that aspect of thinking about the integrated parts and how they coexist and work with each other. And so, as I said, the envelopes, the services, the structure, the skin, the organs, the skeleton, think of it in those terms, and how they integrate together. So, the envelope, just really think of that. What separates conditioned space from unconditioned space, inside from outside. That would be kind of how we think about the envelope, and that's kind of how we seal up our residential structures. So if the garage, for example, is not heated, well, that would be unconditioned space. So we would try to have a tight envelope between the garage and the rest of the house. So that would include the ceiling of the garage, that would include the walls, interior walls of the garage, as well, so that we don't have a lot of heat loss from our house or our building. So there's a lot of different materials that can be put into a wall system, a floor system, a ceiling system that work together in collaboration with each other. And they're subcomponents. So we can think about how they respond to heat, moisture, wind, and those areas. And we've talked about services already in the previous chapter. So we've looked at the plumbing, the electrical, the HVAC systems, and anything that actually cuts through the envelope too we have to consider, because anytime you have something that cuts through something, it's an opportunity for air leakage, and that can lead to moisture leakage as well. And so there's all kinds of issues that come up with that. So our services, the structure, as I've mentioned, is really the building, the bones of the building, the footings, the foundation wall, the walls, the roofs. That's your structure. And some may be solid masonry in older structures, and in newer structures, probably more likely wood frame or some other modifications. We can also think in simple terms that there's major flows that occur within the building that will have an impact on your comfort, the efficiency of the building, and the structural integrity of the building. Really, I think when you think about buildings, if you think about buildings, they're really, once you build them, they're trying to go back to nature. That's really what happens. Like when I first was younger and I'd build a project, I'd think it was going to be like the pyramids and it's going to last forever. And then I quickly realized these structures that you build, they're not necessarily forever. A lot of them, highest and best use, they get taken over. Something else gets built in their place. Also, a lot of, you hear the term, they don't build them like they used to, right? Look at this old building and look at how great this is. Yeah, but for every building that survived, there's probably about 100 or more that have been taken down. Maybe they had a lot of moisture problems. Maybe they weren't structurally sound. They didn't survive. So that's what they call survivorship bias. We think about the ones that have lasted, like why doesn't everything last that long? Well, it's more of a unique element, and it would have had to survive the highest and best used aspect, and it would have had to been built well enough to survive a long time, and then it would have had to been maintained on an ongoing basis over the decades. And there's actually more money that's spent in the ongoing maintenance of our houses and our ongoing maintenance of our buildings than there is that what was actually put in to build it in the first place. And a lot of people don't realize that. It's kind of what they call the iceberg effect, where the amount that you spend on a new building is the part of the iceberg that's above water, and the part that's below water is all the ongoing maintenance and repairs and upgrades that need to be done and performed to maintain that structure. So the three flows are heat flows, moisture flows, and air flows. And so we can think about how heat flows and how moisture flows within the air and how air tends to flow. So, there's these aspects of each individual one. So let's take a look at them. So heat flows, really it's going to move from warm to cold. All right, some says hot to cold. I've got hot to cold there, but it really, something that's warmer will move towards something that's colder, which means in the winter time, your heat is trying to get out. In the summertime, it may be the heat is trying to get in, particularly if your building is air conditioned. So it just flows in that nature, and it's dependent on the surface area, the temperature difference, and the resistance of the material to heat flow. So how big a surface area do we have to the outside? Well, if you're in a townhouse and you're the middle unit, you maybe just have an outside wall at the front and the back, and then you've got the ceiling at the roof. But your side walls, it's neighbors. You've got neighbors beside you, so there's not going to be such a temperature differential between those units. If you're the townhouse on the very end, you have three sides. So the exterior side, the front, the back, and the ceiling. So you're going to have more surface area, so you're going to have more warm trying to move to cold in the wintertime. It also depends on the temperatures difference. So if outside it's 18 degrees Celsius and inside it's 21 Celsius, it's not a big temperature gradient. It's not a big difference between inside to outside. Now, if inside it's 20 degrees Celsius and outside it's minus 20, there's a big temperature gradient. So there's a lot of warm trying to move to cold. There's a lot more impetus for it to do that. And then there's the resistance of the material to heat flow. So we play on that with our buildings in that we try to insulate our walls with a higher R value, resistance to heat loss, with materials that are resistant to heat flowing through them. A piece of steel is a conductor, not only for electricity, but for warm to cold. A piece of styrofoam, not so much. It's got a much higher resistance to heat loss, many multiples higher. So if we can utilize materials like that to slow down the heat flows, that will make us a much more energy efficient building. So we look at those elements and we think about the climate that we're putting it in, the type of building and structure it is, surface area, and the surface area too of what is the surface area? How much of it is windows? How much of it is walls? What's the R value? And that's where you get into the energy modeling aspect too that we talked about in the building systems with HVAC. So you design a system that will ensure that the building is warm in the worst of weather, but at the same time it's running efficiently. And it's designed around how the building structure is. So we do have these heat flows, and we have heat transfers by three methods. So we have radiant heat, we have convection, and we have conduction. All right. So radiant heat is by invisible waves, and radiant it's actually the most comfortable heat. If you sit in front of a fireplace, that's radiant heat. Like, it's a very comfortable heat. The radiators with hot water that run through them, so hot water heating systems that have radiators, it's a very comfortable heat in those houses. So that's radiant heat. If you have hydronics and you have tubing and that's heating your floor, and it's basically creating a warm thermal mass, a very comfortable heat. So we have that. Convection. So when we talked about that in the previous video, which we looked at building systems, and when you think about building systems and forced air systems, it follows the natural tendency that if you heat air, the warm air rises, and then that kind of displaces the cooler air, and the cooler air kind of goes down and the warmer air comes up. So that's kind of how convection heat travels, and it's that very easy flow, but it also can be a little bit drafty too, like a forced air furnace system. It can give you a little bit of, when it comes on, you can feel a little bit of draft. It's not quite as comfortable a heat as radiant heat. And so we got conduction. Well, heat flows, it just moves through materials, like I was saying earlier, with insulating materials concrete is not a good insulator. So heat moves very readily through concrete, and through wood, it's a little bit slower, much slower. And then through insulation, it's much, much slower. So that's why we look at our wall systems. And in the lecture 8C coming up that I talk about, what kind of insulation are we putting in, and 8B, what R value does it have? And then we talk about also the air vapor barriers and what purpose do they serve. So you can think about things in those terms. This is showing a solid brick wall. You know what? Through a solid brick wall, heat travels very readily through it. So you lose a lot of heat in an uninsulated solid masonry house, like half of Toronto is, the older houses. I don't know, there's probably about 700,000 or 800,000 houses like that in Toronto. So there's a lot of heat loss through those structures. New structures, like the Brook drawings that we've been looking at from the chapters in the textbook, Understanding Construction Drawings, we see that they do put a lot of insulation, and we do tightly seal those houses. So there's a lot of advantages to that, to energy efficiency, but there's a few things we have to be cautious about. So moisture exists as a liquid, a solid, and a gas. Water, ice, and vapor. And so usually water vapor can cause the most damage because a lot of times we don't know what's going on with it. Water does cause a lot of damage. You get a flood in the basement, you get water flowing through the roof on a big rainfall, but you usually see it right away and you can usually deal with it. A lot of times water vapor, if it's sort of invisibly going through your walls, reaching the dew point in the air and condensing inside your walls, well, you can get mold and rot and all kinds of things going inside your walls that you're not aware of. So it's a little bit more invisible, and you don't usually know it's a problem till it's a problem. Really, when we think about all of the buildings that I said, and survivorship bias, the bias towards buildings that have lasted a long time, is that most of the buildings that dilapidate and really have major problems, there's been moisture ingress in a multiple of ways, through the foundation, through the roof, through the walls. All of these things are trying to take the building back to nature. You've probably seen some of the documentaries and that on Chernobyl, and you see how after so many years, 30 years or more, how Chernobyl, which has been pretty much abandoned, things are going back to the earth and nature is starting to take over again. It's the way that things work. You go for a drive outside the city and you see these old barns, and some of them are like ready to fall over because they haven't been maintained, and the roof started to go, and then maybe the farmers built a new barn somewhere else, and so then it just slowly collapses and goes back to the earth. That's what's going on. So water vapor travels either by diffusion through materials or airflow. So it can go right through materials. It can diffuse right through like a drywall. But most of the damage is caused by airflows. So usually it's the holes in the seams and the joints and around the electrical outlets and things like that. You get airflows going through. It's not as much of a problem going through the whole surface of a material. Can be in sometimes, but generally not. Generally it's where you've got a pretty tightly sealed building, you've got a few holes, you might get a lot of moisture laden air going through those small areas, and because there's a lot of air flowing through, it's bringing a lot of water vapor in it. And then depending on the temperature, and you'll learn more about this when you study building science in depth, somewhere in that wall, depending on the humidity level, the temperature, it'll hit the dew point and then it'll condense. And if it condenses in, area of like bad insulation and it's surrounded by wood and drywall and that, it can build up moisture and cause mold and rot, which essentially that's what mold is doing, bring it back to nature. So we have these airflows and they're caused by a pressure difference. So you're not going to get a lot of airflow going through holes if it's, 19 outside and 21 inside. Like I said, you're not going to get a lot of airflow. But when you get big temperature differences, you get a lot more airflows. That's why, like in what we're talking about today is more for our climate in Canada. In other climates, what we talk about air and vapor barriers, it might might not be required, or it might have a different parameter around it, because mostly in Canada, the biggest temperature differences are in the winter. We have them in the summer. Like you might have a week or two where it is um, maybe it's 35 degrees Celsius. That's pretty warm in Canada, or maybe 40, maybe even get up to 40. But that's still that inside your house, even if you have it air conditioned, you're probably at like 24 or something like that. So that's a 16 degrees Celsius difference. Well, minus 20 to plus 20, that happens too. That's a 40 degrees Celsius difference. That's a big difference, right? So we have much bigger pressure differentials when we talk about the winter. So you'll hear me discuss things, and I'm really applying it to northern climates. So heat loss, uncomfortable drafts, depositing moisture within the envelope. So it does, when you have airflows and you have a lot of leakage points in the house, it's not comfortable. And it's funny, I should have taken a picture of this house. There's this house, I probably wouldn't like it if I did it, but so there's this house in the neighborhood, and they built this custom home, and like the envelope was like just atrocious. Like I don't know how it passed or whatever. You could just see all the rips and everything. It just was, no care was taken at all. Yet it was probably about a $4.5 million house, and it had this beautiful limestone on the outside. It looks beautiful, but the bones of it, like the envelope of it, not done well at all. Okay, so maybe you think, well, the person's wealthy, they don't care about energy efficiency, and they don't care how much they're paying. But you know what? You're gonna have drafts in that house. It's not gonna feel so comfortable. So uh, you can, if they don't care about energy efficiency, they should maybe care about comfort, and so they're gonna get it that way. And I think the builder just knew whoever they were selling it to didn't really grasp that aspect, or the builder didn't care. Happens. So heat loss, uncomfortable drafts, depositing moisture within the envelope. Wind, sun, rain act from the outside of the house. And of course, very humid times of the year. We talked in an earlier lecture about moisture content and how wood expands and contracts. And when it's really humid for a number of weeks, like in this hot summer, a lot of rain, you get that expansion because of the humidity levels. Well, you know what? How does people live in the house? That can have a big impact too. So, well, maybe not right now, but if there's a family of four and they usually go to the gym sort of thing, and they don't take showers at home, well, you won't have as much humidity because of that. They pick up all their food at McDonald's, well, you probably won't have too much with that. They don't like plants, well, you don't have too much like that. So they're probably not going to have too much humidity going on in the house. On the other hand, you got a family of four and they all take 20-minute hot showers. They cook a lot, make a lot of pasta, a lot of boiling water. They love plants. They got plants everywhere. Those would be things that would drastically change the interior environment. So you'd have a very humid house, warm moving to cold, lots of moisture in the air that could reach the dew point. That would be quite different than a house that was much more lower humidity levels. So how occupants live in the house can really impact that. I saw it myself when we used to do window replacements, our company, and I used to price a lot of them. We used to do a lot of them. And I remember doing a set of townhouses, and one of the townhouses, it was just, we put these new windows in and there was just water just running down the insides. And I'm like, what's going on? I was a lot younger then. And then the next door unit was fine. There was no issue. And then when I thought about it, that one that the water was just running down, the person that lived in there loved plants, and there were plants like everywhere. And so the humidity was building up. It's why when we used to have, before marijuana was legal, there used to be grow ops, and people would get a house and they'd set up all these plants inside. But once that happened, there was so much humidity and mold in the houses, you couldn't even sell the house even after it was done. You'd pretty much have to tear it down. So just how occupants live can change the environment. So R value, you've heard me talk about it. It really is a resistance to heat loss. RSI is just the metric equivalent of R value. And the higher the R value, the more resistant the material is to heat loss through it. So an example of R value to RSI, I still think in the old imperial with R's because it's just an easier number to remember, is this. So R5, R8. like a 1 inch of extruded polystyrene, blue styrofoam SM or code board or Owens Corning code board is about R5, 1 inch thick, which is RSI 0.88. All the insulation that you buy has pretty much both imprinted on it, so it's not hard to see either or. It's just a simple conversion factor between them that really comes up with the numbers. On the drawings that we look at and in the other video that I just did, you'll see it'll list both in the drawings. Thermal resistance. So what's the thermal resistance of the various materials? This is pretty good. It's telling you by thickness how much R value you get. Look at concrete, 0.1 per inch. 0.1 of 1 R value per inch. So you would have to have 13 inches of concrete to have the same R value as you've got 1.3 per inch. So you would have to have, or you can look at it another way. This is 0.1, this is 1.3. It's 13 times the R value is lumber compared to concrete. And then lumber is not even that great, right? Look at the difference with the different insulations. And fiberglass 3.4. Some of the newer fiberglass that you'll see, like that's listed on the Doncaster drawing, is higher than that. I think it's around 3.9 R value per inch. So to get up to R24 or R22.5, whatever it is. So the R value is significantly more, like that's 32 times more than concrete. So that's why I'm saying it's such an important aspect to pay attention to the envelope if we are striving towards getting towards net zero housing and net zero ready, where the envelope is basically ready for the renewables. That's what we need to do. And so this just gives you a pretty good idea of differences between board insulation, extruded polystyrene, that would be your blue styrofoam or your Owens code board, R5 per inch, which is better than expanded polystyrene. Expanded polystyrene looks like the white styrofoam coffee cups. I think I got a picture in the next lecture coming up of it. But it's only around, I think, around 3.6. So there's differences between the different R values. The same thing with spray foam. You can have ½ pound or you can have 2 pound, and the ½ pound doesn't have nearly the R value per inch that the 2 pound does. But they have different advantages and disadvantages too. So you have to look at what it is that you're after. So 3 key components to keeping the heat in are the air barrier, the vapor barrier, and insulation. And so we have these 3 components. And the air barrier really is about, well, one of the things you got to know is that an air barrier could go on the inside or the outside of the building. So in our neck of the woods, it can go on the inside or the outside. The vapor barrier has got to go on the warm side of the building. All right, so it's got to go on the warm side of the building in our climate. And to make it even more complicated, the air barrier can also be the same material as the vapor barrier. So if we're going to put it on the warm side, and we've got a vapor barrier has to be on the warm side, well, if we tightly seal the vapor barrier, which is usually like this plastic poly, 6 mil polyethylene, we tightly seal it, then it can also be the air barrier. And so what the vapor barrier does, it stops moisture diffusion. Remember we said earlier, diffusion through a material? And what the air barrier does, it stops airflows. It stops airflow. So it needs to be very tight. Vapor barrier just is really a function of surface area because it's looking at diffusion through materials. Whereas the air barrier, we're looking at holes. We want it to be tight. And you can put the air barrier on the outside. Very typically, like especially production builders, they put it on the inside with the vapor barrier. So when we think about, we can make air barriers out of a lot of different components. And there's a lot of different systems and ways of doing it out there. I'll leave that to some of your building science courses. You can discuss that and look at those types of things when you follow up on something in more depth. But you can use a lot of different means and ways of achieving an air barrier. And as I mentioned, it could be part of the air vapor barrier systems when placed on the warm side, uh, as must be when it's a vapor barrier. It can be on the outside, but it has to be continuous. So if you've got it on the outside of the building, somehow you got to lap it around because you got the ceiling on the inside. So you'd have to basically go through the plates and have it lap around so you could seal it all the way around. So if you're going to put it from the outside, you also have to connect it to the ceiling, second floor if it's a two-floored house. So you have to connect it to the ceiling air vapor barrier. So if you've got, for example, a Tyvek or a Blue Skin approved air barrier material you use on the outside of the building, has to connect through the plates to the air vapor barrier that you would use on the ceiling, because that's where you would need to put that one. In that case. Actually, I think Tyvek has some pretty good details on their website. Maybe I should have looked that up before I did this video, but some very good details on their website of how you can run it as a air barrier. And I would imagine Blue Skin would have the same idea. So I'm not promoting any one supplier over the other. It's just these are some examples. So this is like where, in this particular case, the Tyvek is on the outside. I'm quite sure that they're still using the poly on the inside, the 6 mil, as their air vapor barrier. And in this case, they're using it as a weather barrier, the Tyvek on the outside. So that means they don't have to seal it through the plates to connect it to the poly on the inside ceiling. Because the poly on the inside ceiling is all connected with the walls. But there is absolutely nothing wrong. This is actually good, like sealing all the joints all around with the Tyvek. It's for moisture protection, but it also is acting like a secondary barrier for airflows. So that's really good from that perspective, that you've got it acting as like a secondary barrier for airflows. Can't lose on that side of it, because one of the things with an air barrier material when it's applied to the outside is you got to think of it like it needs to be able to breathe. You do not want to put plastic on the outside of your building. Somebody would get the bright idea, oh, why don't I just put plastic on the inside and the outside? You don't want to do that. You want to make sure that it breathes, because no matter how good you are, moisture will get into the wall system. All right, no matter how tight you make it, there will always be some moisture getting into the wall system. And what you want to do is, if moisture gets in, you want to provide a way for it to get out. So if moisture gets in, you want to provide a way for it to dry out to the outside. And that's going to make for a much more healthy, longer lasting building from that perspective. It's like we talked about when we did the masonry. That's why you got a 1-inch airspace. If water gets in, you want it to be able to get out. The best systems allow for some problems and for it to still be able to correct itself. So that's very helpful from that perspective. So it's like a ski coat. You know, if you buy a cheap ski coat and it's like a raincoat, when you're out there, what happens? And it's really cold and you're skiing and you're out and about, you're sweating, and that sweat becomes wet, and then you get chills. If you have a really good ski coat, the wind can blow on you. The wind doesn't go through it, but at the same time when you sweat, your sweat dries out and it evaporates. All right, the warm goes to the cold, but it evaporates. That is a good system. And so this is, you think about it along those ways. That's always the way that some of the scientists that I worked with at U of T would explain it. And pretty much the vapor retarder provides the protection to the structure. You don't want moisture going through the wall, so the vapor barrier protects the surface area aspect. Even the building science side of things, there's a lot of debate on, you know, the necessity of that. Even an older building, if you have enough coats of paint on the wall, it's probably stopping the diffusion through it. But the building code requires it, so you have no choice. So you've got to put that vapor retarder on the inside of the vapor barrier, the 6 mil polyethylene, and it prevents that moisture-laden air from going through the wall. And then if we've tightly sealed it, the air barrier stops the air flows through it. All right, so you can think of it that way. And polyethylene. These are some of the different materials that can be used. You know, like I said, you can get vapor barrier paint. You can vinyl wallpaper. There's a very interesting example that buildingscience.com. If you're interested in this area, buildingscience.com is an excellent website. They had a case in Arizona, and it was a motel, and so they had vinyl wallpaper on the inside of the walls. Well, in Arizona, it gets very, very hot, and it's pretty dry. It's like semi-desert, and so they were doing some work and taking off the wallpaper. They took off the wallpaper. On the inside of the wallpaper was pure mold. Everything was mold, and they were like, "We're in a desert. How are we getting mold? You need like humidity for mold." And so what was happening was they didn't have what they call zero landscaping. They had like grass and stuff, and they had sprinklers, and the sprinklers were kind of hitting the side of the house or the motel, and then the sun was out while it was hitting them, and they had basically sun-driven moisture and heat-driven moisture because you got the sun, it's against the wall, it's hot, and you got this spray of water going against it. There was a big pressure differential from the warm to the cooler side, which was air conditioned, and it diffused through the outside material right through to the back of the drywall, and then it condensed. So that was kind of the vapor barrier coming from the other side. So it's just how what we were talking about, air flows and moisture flows occur, and having a good basic understanding of why that would happen. So theoretically, it's more critical to have a tight air barrier than vapor barrier. And as I said, you can have combination on the inside. So here's some details from the best practice, CMHC Best Practices Guide, Canada Mortgage and Housing Corporation. And this is just showing you, and you can follow when it says VR, vapor retarder, when it says AB, air barrier. And so like a header wrap, see how it goes down around the plate, up over top of the plywood and up the wall. And then they got an acoustic sealant between this would be a Tyvek paper because it's on the outside. You don't want plastic on the outside, right? So spun bonded olefin. So like a Tyvek material would be a spun bonded olefin. And so this would seal that, and then it would seal against the vapor retarder. So we call this a header wrap. All right, it's going around the rim joist, around here to seal these areas. And a lot of times it becomes damaged, so it should be fixed before things are closed up with a tuck tape, which is the red tape that you see everywhere. So very typical. And you can see other things that we've discussed too in the course. You can have then on the outside of the material, you can have some sort of building paper. So if it says asphalt building paper, that's the regular building paper, but you could put a Tyvek paper on the outside. That would be even better. Here's another example. These are always sore points, like behind bathtubs. You got to plan your envelope to make sure that you have access, right? Once the tub is in, you're never going to get back behind here. So you got to make sure that things are sealed properly before the tub ever goes in. And this is your brick ties if you're wondering what those are. This is looking at it down. So you're looking at plan view. These are sections. So this is your floor joist. That's your bathtub. This is your bat insulation in the wall. Here we have at the end wall. So then this would have on the inside, that's your, you probably saw it in some earlier pictures in the book where you see black poly. So it's wrapped around a strip so that then when you have this intersecting wall, you can tie the poly in this room to it with an acoustic sealant. That's why it has to be a continuous air vapor barrier here. It is, because it's sealed and it's sealed. And then if there's like wires that go through, like for an outdoor light or something, then they need to be sealed, all the holes. Remember, AB means air barrier, VR means vapor retarder. All right, and MB is moisture barrier. So the building paper on the outside. So here you go. And this isn't all that great. done, but you can see the tuck tape, you can see the poly, you can see how it's wrapped around the boxes. As I'll show you in a minute, you can do better than this because there's special boxes that self-seal. These things leak like a sieve. They're always a challenge, those kind of electrical boxes. In many cases too, if you're going for like a net zero design, your best bet is to try to design it that you have as few boxes and protrusions on outside walls. So don't put a switch box on an outside wall, put it on an inside wall if there's an intersecting inside wall that's nearby. I've even seen with some net zeros designs where the outlets are into the floor, so they're floor outlets, special caps so that you can plug into the floor. That way you don't penetrate the envelope. And again, the tuck tape would seal over any particular joints that occur in. This part here is inside. This part here is outside. So this is actually that section of the Doncaster house that you have the drawings for that sticks out. And so there's a second floor above this, but there's no second floor above that. And it has to be approved material, so it has it printed on the poly, so an inspector would quickly be able to tell. This is your header wrap that is coming up from the floor. So what we were looking at over here, that header wrap coming around the floor and up here, that's it right there. And that's why it's the Tyvek type paper that's coming up and around. Here we have your, this is a better one. It's got like a self-sealing gasket that pulls through, and then this gasket seals around the outside of the outlet box so that there would be very little leakage through those outlet boxes, as opposed to this, which is very difficult to seal that really well. Here's where you can see acoustic sealant's been put into place to seal around the wires, where the poly, where the attic is in this case. You can see the black poly here. That's wrapped around to make a continuous barrier. This would be a top plate, so there's another plate there, and I'm assuming that you just can't see where it's sealed, probably just above there between the two with acoustic sealant. So places where you've got things like exhaust have to be sealed up so that, again, it's tight and you don't have losses through it. You can see the air vapor barrier. Where you got something like a fireplace, always notorious, even the high efficiency gas fireplaces, trying to get that all sealed up. You kind of have to plan how you're going to do it. So they put the air vapor barrier in and the drywall inside as they were constructing it to ensure this was tightly sealed. This was an Energy Star house, so they were making sure that it would pass the blower door test. It kind of follows that process. And again, you can see here, and this is stopping, I think, in this part over here, it's not outside, but this section here, the house is an outside wall. So the outside wall stops here somewhere, and then your inside wall. So that's why you don't see it. You also see the bad insulation tucked in along the top here, and then this gets sealed here. Because the other thing is, the reason you put a header wrap is you'd never be able to tightly seal in between all of these. So this is just acting as, in these sections, this is acting as a vapor barrier, right? It's not acting as an air barrier. But they usually will have, if I go back a few slides. So in this section here, this is acting as an air barrier, right? In this part, the poly that you saw, they don't draw it that well here, but the poly that's coming up inside, it's acting as a vapor retarder. So only at these points do they separate out, because they know they'll never be able to get that tightly sealed around those, I'll get to it, those points. Like you can never get that all tight in between each, you'll never get that tightly sealed. But around a header wrap, much easier, much more possible. So it kind of gives you the intro and the idea about how that works. And as I mentioned, this is the Doncaster house. So this is that close-up of the living room here. There's essentially a roof over this section here, steel beam going across. These kind of intersections, they are always difficult to really tightly seal. And that's a challenge. And as we move to net zero, those things get to be more challenging, but more fun in a lot of ways too. And once you get it down to a system, it's like companies like Mattamy Homes and many others, They standardize that the minimum they do is like an Energy Star house, and that's like typically 25% more energy efficient than the current building code. Once you systemize it, you're able to do it without it costing a lot more money. You just educate your workers, you build in systems, you make sure it's done a certain way, and then it just becomes second nature. So I don't really fathom why $4 million houses that are being built, custom homes, and I see these, leaky envelopes, and they're going to be uncomfortable. They're minimum building code requirements really wouldn't be that much of an effort. And the problem is the buying public doesn't necessarily know the difference and demand it, and that would make a huge difference for us and in reducing our carbon footprint. So that's what I wanted to cover in this lecture. I've got another little one which will be more on insulation, and we'll see you soon. So this is Tom Stephenson signing off for now, and have a great weekend.